All right, guys, you did it. We did it. We are on the last unit. So basically, it's going to be this unit is called steady state analysis with the capacitors and inductors. So it's kind of like the first unit where we did a steady state analysis, but of DC batteries and DC, components. However, now we're going to introduce time varying voltage sources, current sources, and stuff like that with capacitors and inductors. And we're actually going to have multiple capacitors and inductors. But for this video, I kind of want to stray away from the electronics, the electrical engineering portion first, and I want to talk about some basic math stuff first, because I feel like thankfully I was able to have a pretty good foundation in this, but a lot of the times when I talk to some of my classmates and stuff like that, they get a little confused on the notation and stuff. So this is basically, this lesson, complex numbers in polar form, is just going to be a review of complex numbers in polar form, because that's generally how we're going to look at all of this. So we're going to basically be looking at all of this in vectors and coordinates, which are in turn gonna be interpreted as like circles and triangles. So first of all, what is a complex number? This is a complex number right here. And a complex number basically has a real part and imaginary part, okay? This J is mathematically equivalent to root -1. And for our purposes as an engineer, because we're going to look at this at an engineering perspective, not a physicist's perspective, but basically we're just saying that this is here because if we have two components, we can store more information. That's essentially what my professors told us, is that like for our purposes, we don't really have to think about it as root -1 unless we're doing explicit math on it. Okay? And actually, because this is a vector, we can write it in a grid form where the y-axis is imaginary and the x-axis is real. So this would represent the vector 3, 4, right? And so this is where like the triangle idea comes in, okay? And then the circle idea comes in when you can go around it, okay? But we'll talk about that in a little bit. And so right here, it's the same thing. I'm not going to draw this to scale. I'm just going to draw it like, so we're going to go 6 in the x direction, or 6 in the real direction, and -8.5 in the imaginary section. And so our vector is going to look like that. Okay, so this is what that complex number represents. Okay, the next thing that we need to know is the complex conjugate. Now the complex conjugate is just, if you have a complex number A and it looks like this, like these guys above, then the complex conjugate, which is denoted with this asterisk, is the complex, it's a complex conjugate A minus JB. So every single time that you see a J, you're just going to stick a negative sign on it. And that's useful. Well, actually, first, let's look at the complex conjugate of this guy. So the complex conjugate of this guy is just going to be 4 plus J6, because you got that plus action going on right there. Now, this one's a little interesting because, actually, no, it's not interesting. Sorry, I'm getting ahead of myself. The complex conjugate of this guy is just going to be, our everything negated, every J thing negated. So it's just going to be this. Okay. So we're going to take all these j's and we're going to just put a negative sign in front of them. And this is the complex conjugate, A star. Now, the next thing that we have to do is finding the magnitude and phase and converting to polar form. If you guys remember polar form, hopefully y'all do, polar form is basically like we have the Cartesian system, right, which we graph the vector and stuff like that. Well, we can graph the same vector on the polar form, the polar grid, right? And so we can look at this in the terms of an angle and an amplitude, okay? And thankfully it's very easy to go from Cartesian to polar, and you're just going to use the Pythagorean theorem for the magnitude, and that's because we say that this right here is A and this right here is B, okay? And then for theta, we're going to use, well, I used phi. So these are interchangeable. Oftentimes you're going to see phi or this kind of phi. I'm pretty sure they're the same thing. And then theta, you know, you're going to see those kinds of guys that are going to be represented here. And so that's just going to be B over A. Yeah. And so we can actually take these formulas and we can have our Cartesian and we can turn it into a polar representation, okay? And then we'll get this guy right here, okay? And you have to know also that this phi is dependent on the quadrant, okay? So we have quadrant 1, 2, 3, and 4, right? So on a normal calculator, these guys are going to be covered, okay? These guys are covered by the calculator, and you're not going to get the wrong answer. Now, if your vector turns out to be in one of these directions, then the calculator is going to give a not simplified form, but it's going to give an equivalent form on this side, okay? And so when you report your answer, you need to make sure that you draw it out. That's why we drew out the vectors here, right? We drew the vectors here, right here, because I wanted to show you guys that they can be in different quadrants, and that actually matters because phase matters, because that's like cancellation and stuff like that. So we have a little exercise here, and we're going to write the polar form of the above complex numbers. So essentially what they mean by the above, we're going to look at this right here, and we're going to look at this one right here. We want to find the polar representation for this, and so what do we need for the polar representation? Well, we're going to need a magnitude, and I'm just going to call it A, and so that's just going to come from 4 squared plus 6 squared rooted is equal to root 52. Now, oftentimes I'm probably going to be writing it in a decimal form with 3 significant figures, just cause this is not a chemistry class, no one cares. You can report it like this, or you can report it like this, and you can write all of the numbers up to the 20th decimal if you really, really, really want to. Now we're going to find the phi, okay? So we're going to say the tangent inverse of B over A, and B in this case is 6, and it's a negative 6, so we're going to have that right here, over 4, and that is going to equal negative 56.310 degrees, okay? And we know that this is in the 4th quadrant because we have the negative y value right here, so it's gonna look something like that, okay? And when we put it into the phasor form, polar form. Phasor is a term that we're going to define in the next video. It's going to look like 7.211 7.211 e to the negative j 56.310 degrees. And we are going to be using degrees, not radians. Or you can write it in this format. I'm going to use the radical this time. 52 angle of negative 56.3099 degrees. That's another convention, but I am going to be using this way. Okay. Now for this one, we're actually going to have to use the complex conjugate because we cannot find the magnitude of these two guys in this form. So what we're going to have to do is we're going to have to multiply by a factor of 1. So we're going to multiply by the conjugate of the bottom because, oh, I completely glazed over this. When you have the a, the conjugate of a times a, you're going to get a real number, and you're going to get this identity right here. And so you're just going to say a squared plus b squared. And so for here, we're going to multiply both sides by some factor of 1, and that's just going to be the complex conjugate of the denominator, because we want the denominator to be a real number. And we want the denominator to be a real number so that we can simplify this into a real and an imaginary portion, okay? So we're going to multiply this out, and we're going to just use the distributive property for the top. So that's 30 j20 plus j18 plus, but actually this is going to be minus because now we're going to use j squared is equal to negative 1, because root negative 1 times root negative 1, the roots cancel out, and we're going to get 12, and we're going to divide, and we're going to say 6 squared is 36 plus 16, and 36 plus 16 is 52, and so we're going to get 18 plus j38 over 52. And so we are going to get 18 over 52, which I've calculated to be 0.346 plus, and then 38 over 52, which is going to be 0.7307. And that's going to, so this is the rectangular form that we wanted. Now we can easily find the amplitude, which is 0.346 squared plus 0.7307, all of that with a square root, and that is going to equal 0.808, okay? And the phi is equal to tan negative 1 over 0.730 over 0.346, and that is going to equal 64.65 degrees, okay? And so putting it in our polar form, it will look like 0.808 e to the j 64.65 degrees. And this is going to be located in the first quadrant, okay? So very simple stuff right now, okay? But that's the answer to that. And we're going to have one more example, and basically we're going to do everything that we did earlier, and we're going to simplify these a little more complicated complex numbers. So right here, once again, we're going to multiply by our complex conjugate so that we can remove the, we can put everything on the top and put it into our Cartesian coordinate system. So we're going to multiply everything by the complex conjugate of the bottom. And from there, we are going to get 4 minus j 3.5. And if we do our little quick thing, 4 squared is 16 plus 3.5 squared, and 3.5 squared is 12.25. And so that will simplify down to 0.14 minus J 0.868. We're going to find the complex amplitude, and that's going to be 0.1415 squared plus negative 0.123 squared, and that's going to equal 0.8799. And for our theta or phi, whichever one you choose, we're going to get the inverse tangent negative 0.123. Oops, I accidentally wrote the wrong number right here. That is actually supposed to be 0.123, so 0.123, and divided by 0.1415, and we're gonna get negative 41.1859. And when we put this into our form, the answer will be 8799 e to the negative j 41.1859. I did these calculations earlier, and I have my calculator out right now, but I guess I made some mistakes while doing this as well, but this should be the right answer. Now we're going to draw the little plot of what this generally looks like, and we have a negative imaginary value, so we're going to go down and to the right because we have a positive real value, so it's going to be located in quadrant 4. So whatever our answer was from the calculator is correct. Now for our last problem, we're going to do the same thing like so, and we are going to multiply across the top, so it's 6 minus 24j minus j7 plus 28, or minus 28j, 28, just 28. And then at the bottom, we're going to have 1 squared plus 4 squared is 17. So simplified down, we're going to get negative 22 minus j31 over 17, which simplifies to negative 1.294 minus j 1.8235. Now, you should be on edge right now because this is in the third quadrant, because we have both negative coordinates, and so it's going to look like this. So let's go ahead and actually, with that in mind, we're going to go ahead and actually calculate the amplitude. And so the amplitude is just simply going to be 1.294 squared. And I'm not going to write the negatives because they're already taken care of, but I would highly recommend that you do, so you don't forget that that's actually what you're putting in here. And then that's going to turn into 2.236. And then when we do our theta, we're going to get tangent negative 1 over, and then right here, the negatives do matter. We're going to have negative 1.8235 over negative 1.294. And that's going to give us 54.6375. But if we look at our representation, that number is going to be right here. Okay? That's wrong. We're saying that our vector is actually this black one right here. So we're going to have to add 180 degrees from that, or subtract 180 degrees from that. Okay? It doesn't matter which one you do. Those are both equivalent, but this is not equivalent. Okay? It's you're wrong by 180 degrees. And that was something that I've had to play around with, right? Because a lot of the times professors will just say, add 180. And you're like, why? Well, they don't really amply explain it because they expect you to know that. And you should know that. But I want to make sure that everybody here, doesn't make that kind of a mistake. So we're going to add 180 degrees. And so our actual answer is going to be 234.638 degrees. And so our final result is this: 2.236 EJ234.638 degrees. Okay. And so that's just a brief refresher and review, essentially, of these complex numbers in polar form. We're actually going to assign electrical values next lesson, and that's going to be like more signals and systems. Then it isn't until the third lesson that we're actually going to bring back our nodal analysis and our loop analysis, and we are going to calculate the capacitors and the inductors and the resistors in their various configurations in that steady state form. So last time we had a transient form where we saw that what happens if we have a switch, right, going between the two sections. This time we're going to look at what is the behavior of this circuit when it's been a really long time. Okay? And yeah, that's it.